So our last speaker is Mr. Anvar Kacimov. He's going to present Dipolic MAR bubble inside confined brine formation or floating lands on top of unconfined saline aquifer. Mr. Kacimov, you have the floor.
Thank you. First, it's my pleasure to acknowledge the contribution of my co-authors, Dr. Abnosov, Kazan University, Russia, and Dr. Al-Maktoumi from Sultan Qaboos University, my colleague, and the sources of funding also acknowledged. So my presentation, the plan is shown here, actually the core of our work was mathematical modeling, but I realized when listening to the presentations of others and looking at the posters, none of them had any partial differential equation even mentioned, right? So, and what we did, we solved partial differential equations, boundary value problems, and this is what we actually did in this work. But I will shorten this part of our work and talk mostly about applications rather than the machinery of mathematical solutions. And so as an introduction, I'd like to object the historical picture which has been given at several presentations in the workshop on the first day, when the map of MAR has been shown and the Soviet Union was absolutely blank space. And this is not fair, and it is sad to me as a Russian communist that so all the history of MAR in the Soviet days has vanished from the records. And I will present two cases which stem from the Soviet experience of MAR. And this is point number 2 and point number 3, and 4, 5 are just short conclusions. So briefly about Oman also, this has been already discussed. UAE, Oman, so absolutely the same climate, hyper-arid, so the desert. And we have MAR as a necessity. It's not for fun, it is a necessity. Because of severe deficit of fresh water, so about 400 million cubic meters per year on the national scale. And treated wastewater as a source of MAR has been approved by the government last year, right? So they gave a green light, right? So on the national scale to expand MAR projects with treated wastewater. One project in Salalah Plain in the south of Oman was partially successful. So and now, so from the conference, I realized why, right? So a colleague from Arkansas introduced the term slippage, right? So and so here, so in this project, farmers a percentage of slippage of groundwater after injection through a gallery of wells was more than 100%, and it actually destroyed the purpose of the MAR project to mitigate the seawater intrusion in the Salalah Plain. And then the government became very cautious to expand this treated wastewater as for MAR injection. Right, so this is a table showing the history, the forecast of what is expected to be as treated wastewater from the National Water Treatment Company, 800 million cubic meters per year. This is our last red light highlighted figures. Right, so but with runoff, right? So there are no limitations. Moreover, the Ministry of Water Resources invested huge money, constructed now so more than 45 dams. This is 2015 figure. So they are recharge dams specifically for managed aquifer recharge or artificial recharge of the aquifers, and we work with this rainwater infiltration through the reservoirs of these dams for quite a long time. So we have several projects. We published a lot of theoretical and experimental results, right? So, and have collaboration projects with our colleagues from other countries in the OMAN region, and we learned from, say, Jordan and other countries how treated wastewater is recharged, and so we expect to implement this experience in the forthcoming projects in Oman with treated wastewater disposal. So now the Soviet experience, right? So this is a project which started in the 1950s actually, and in Turkmenistan, the Central Asian Republic, now independent, and we published just recently a paper which I gave a long quote, right? So where the referees, right? So the American and Dutch experts acknowledged the pioneering technology of ASR, right? So MAR and ASR in the deserts of Karakum, right? So in this Takiris is a Turkmenian word, it's an infiltration basin in English. Right? So the technology is very simple, right? So the freshwater lens is created on we call it floating freshwater lens, right? So by infiltration, right? So from a recharge basin, right? And the continuous or periodic input from the infiltration zone is intercepted by evaporation. Usually, so these types of lenses in Holland or in the US, seldom evaporative losses are counted. But here it is for natural lenses, it is the only source of water loss, right? So from the lens, infiltration and U-turn of in the saturated lens, and then water leaves through evaporation and transpiration because vegetation, lush vegetation emerges on the periphery of the lens, on the surface. Right, so this is a set of photos, scanned images from the book, right? So by a Russian academician Kunin in 1959, he published a book, and then many other books and papers were published, including papers in English, how these lenses were replenished and how water was pumped out from these lenses with a very smart control of the interface, sharp interface. No, in reality it is not really sharp, right? So it is shown here in the isoconcentric lines, right? So and this dual pumping, so by vertical wells and which withdrew both saline water and fresh water from the lens, right? So came to this type of water management from the oil industry. It was the technology has been developed in the 1940s by the Soviet oil companies, so-called dynamic control of the oil-water contact. Here, mathematically, it is the same problem, right? So water and oil, or water and brine beneath, right? So it is the same. Right, so this is our diagram, right? So our scheme, right? So what is schematization? Is a vertical cross section, right? So the novelty here in this work is that the evaporation losses, right? So we consider as depending on the depth of the water table. The higher the depth, the smaller the evaporation losses, because in all standard models, evaporation rate is considered either constant or decreasing linearly with time. So, and we managed to solve the problem with arbitrary function of evaporation losses as an arbitrary function of the depth of the water table. And this is a solution. I will not bother you with this solution, right? So we managed to get the position of the water table or phreatic surface, the sharp interface using the Dupuy-Forchheimer assumption and the Gibbon I forgot the names, the German and Dutch scientists, right? So Gibbon Herzberg, right? So the assumption. So the sharp interface and the phreatic surface are obtained in this is an explicit analytical solution. And the volume of the freshwater lens and the extent of the freshwater lens are obtained, right? So from this analytical solution. And the second example from the Soviet experience, and it may go to the taxonomy of Dr. Pine, right? So who pointed out number 3 MAR type or ASR type, so for contingency planning, so for the cases of say nuclear wars, right? So and here, so what we did 30 years ago, right? So now, later I learned that it is called MAR in English, artificial recharge or MAR. So on that days we didn't use this terminology. What is shown here is it's a bunker, right? So it's a silo, right? So and commanding point of the intercontinental ballistic missiles, right? So it's a depth of 30 meters, right? So confined aquifer, and the task is to supply water, right? So because of the war exigencies, the expected contamination of the surface water and even groundwater, right? So the circulation of treated wastewater, instead of using what we use in standard sewage treatment plants, it's a big unit, right? So filtration unit, vertical filtration here. So we suggested a method which is based on so-called dipole, right? So on the top, the vertical line shows the bottom of the bunker, and now we use hydrogeological terminology. We call it caprock, right? So, and then we place a sink and source, right? So at a certain distance between them, and this is a mathematically dipole. And in applications to saline and brine aquifers in Oman, in several aquifers, we have TDS of 80,000, 100,000 milligrams per liter. It means it's a heavy brine. And actually, it helps to keep water, so this confining interface helps keeping water so floating, right? So and this bubble, right? So fresh water bubble, right? So is bounded from the top by the bunker bottom, and on the at the bottom it is subtended by sharp interface, and we obtained an analytical solution for this case, right? So and the wells are horizontal, right? So these are not vertical wells; they go along the bunker bottom, right? So and steady state solution, right? So we circulate continuously fresh water within this volume, right? So, and it is filtration and storage, because the bunker volume is limited. We cannot store there filtration cartridges. And this is an extension to the case of now it's confined aquifer. We have caprock, bedrock, and the same bubble, right? So, and analytical solution is again obtained in an explicit form, right? So, and all these solutions are compared with numerical modeling, analytical solution, and these are solutions obtained by seawater, right? So density dependent flow, and there is a good match between the analytical and numerical solutions. Well, and this is my poster, right? So which I'm presenting. It is also related to a new technology of infiltration, right? So, but I will present the poster tomorrow as an oral presentation, and I'm concluding with what is a summary of our work. That smart or intelligent design in Mars systems should be based on analytical and numerical analysis, which should precede the design and implementation of the project. No, and we hope that our solutions, our theory, passes this criterion of simplicity, right? So the MAR systems should be simple for implementation, so because too complicated systems are not sustainable, right? So and mathematics should be simple, and simplicity here. So I relate to my favorite quote from Kalashnikov, right? So it should be as simple as Kalashnikov gun, right? So and because in Oman, right? So the government decided to go ahead with treated wastewater disposal in MAR projects, right? So we are ready, right? So we have in our research group all the resources, right? So the theoretical, we have lot of equipment, we have good relations with collaboration with colleagues from different countries. Last advertisement of our conference, please put into your calendar, right? So next year in March 2020, we are organizing a conference on water resource management in arid countries, and the MAR section will be definitely an important component of this conference. Welcome to our conference. Thank you.
Thank you, Mr. Kacimov. We have time for a couple of questions. Anybody, please? Thank you, Anvar. So we are finishing the second part of the session 8. It will follow after lunch with some poster presentations, and there are some poster presentations also outside related to this session that you should visit or could visit or may visit rather during the coffee break. The next session will be chaired by my co-chair, José Antonio de la Orden, as I am attending the votes for the best poster of the ISMAR 10 to be mentioned later in the plenary. Thank you, all of you, for coming. See you later.